Okay, welcome back. Let's dive straight into this explainer and build a rock-solid visual toolkit for tackling the absolute toughest 3D geometry solids you're ever going to face in your Cambridge 0580 mathematics exams. Now look, I see two types of students every single year. Let's call them Alex and Sam. Alex is the overloader. Alex tries to memorize every single raw mathematical fact, every obscure formula, but applies absolutely zero underlying strategy. And then there's Sam. Sam rushes. Sam sees a shape, misses the command word requirements entirely, grabs the first number they see, and dives into a calculation that is doomed from step one. If you have ever looked at an exam question featuring a cone stuffed inside a cylinder and felt that immediate wave of panic, you are in the exact right place. We are going to strip away the confusion. We are going to look at exactly how these 3D shapes function, using core formulas as our ultimate building blocks, so you never fall into the traps that catch out Alex and Sam.
Here is our strategic roadmap for today. First, the geometry of spheres. Second, unlocking pyramids. Third, cones and slant heights. Fourth, slicing shapes, which introduces the frustum. And fifth, tackling composite solids. We're going to build our structural knowledge logically, literally block by block. We'll start from the simplest, single-variable shapes and systematically work our way up to those high-mark, complex composite structures that make or break your final grade.
Section 1. The geometry of spheres. Let's jump in.
Let's start with the most mathematically perfectly rounded shape in the universe, the sphere. Now, what's incredible about a sphere is that it relies entirely on a single variable, just one, the radius. In the world of spheres, if you have the radius, you hold the key to literally everything else. But this is exactly where we need to apply our answering framework. We can actually adapt a popular essay framework here, PEL. That stands for parameters, equation, execution, and link. First, identify your parameters. Are you looking for volume or surface area? Understanding this brilliantly illustrates the difference between finding the 3D physical space inside a sphere versus the 2D wrapper covering the outside of it. Notice that finding the volume requires the radius cubed, multiplied by the fraction 4/3. It's a three-dimensional metric, so we cube the parameter. But when calculating surface area, you're essentially just painting the outside. That is a two-dimensional task. So naturally, the equation uses radius squared and a multiplier of 4.
Now, before you start stressing out and trying to flashcard all these numbers, let's stop for a second. Here is an absolutely crucial piece of assessment reassurance, directly from the Cambridge syllabus. The formula for the volume of a sphere will be given to you in your assessment. This is where the student we called Alex goes wrong. Alex spends hours rote memorizing formulas. But the examiners aren't testing your memory. They are testing your execution. The formulas for the volume and surface area of a sphere are going to be sitting right there on the front page of your exam paper. Your goal is knowing exactly how to maneuver and apply these formulas algebraically when you're put under pressure.
So, let's look at the execution. The crucial high-grade point here is knowing how to work backward. An exam paper is very rarely just going to hand you a radius and ask for the volume. That's a one-mark question. Instead, they'll give you a scenario exactly like this. A steel ball with a volume of 600 cubic centimeters is melted down and made into 3 smaller balls in a 7:5:3 ratio. How do you find the new radii? First, you find the total parts of the ratio. 7 plus 5 plus 3 equals 15 parts. Divide the total 600 volume by 15, and you get 40 cubic centimeters per part. So, the biggest new ball is 7 parts times 40, which is 280 cubic centimeters. Now, here is the magic step. You set that 280 equal to the formula, 4/3 pi r cubed. From there, you just use basic algebra to isolate r, dividing by pi, multiplying by 3/4, and finally taking the cube root. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. Unlocking pyramids. We are leaving the perfectly curved world of spheres and entering the highly angular world of polygons. Let's look at the pyramid. A pyramid is a shape strictly defined by two things, a polygon base and a shared vertex. Whether the base of your pyramid is a simple square, a long rectangle, or even a complex hexagon, every single one of those sloping, triangular faces must travel upwards and meet at one single solitary point at the very top. In geometry, we call this the apex. The apex is the absolute defining structural feature of the pyramid.
Now, I want you to burn this specific fraction into your memory. 1/3. This fraction is the absolute, undisputed hero of all pyramid calculations. It honestly does not matter what kind of crazy polygonal shape the base of your pyramid is. Whenever you are calculating the volume of a pyramid, this fraction of 1/3 is the constant multiplier you must never, ever forget.
But why 1/3? We don't just want to memorize, we want to understand the logic. Imagine a standard cube. By dividing that perfect cube from the center outward, we can actually create exactly 6 congruent square-based pyramids. Through this, we can mathematically prove that any pyramid's volume is exactly 1/3 of the prism that tightly encloses it. Think of it this way. If you have a square-based box and a pyramid with the exact same base size and the exact same height, it would take exactly 3 of those pyramids to perfectly fill the box. No more, no less. So your formula is always going to be 1/3 multiplied by the area of whatever the base shape is, multiplied by the straight perpendicular height.
Section 3. Cones and slant heights.
Now let's transition into a shape that is, quite honestly, just a pyramid in an elaborate disguise, the cone. A cone operates on the exact same fundamental principles as a pyramid. It simply swapped out the polygon base for a circular one. But this brings us to the biggest trap in the entire syllabus. This is exactly where our rushing student, Sam, loses massive marks. Exam questions will constantly try to trick you by mixing up the internal vertical height, denoted as h, with the outer slant height, denoted as L. The vertical height h drops straight down from the apex, dead center into the middle of the circular base. It's perfectly straight. The slant height L, however, slides down the outside curved edge. The absolute key here is visualizing that these two lines, along with the radius at the bottom, form a perfect right-angled triangle hidden right inside the cone.
Decoding the command words in your exam is how you avoid the trap. Are they asking for internal space or external covering? Notice how calculating the volume requires the internal perpendicular height, h. Volume is about filling the inside space, so you need that straight vertical drop to measure how tall the space is. The formula is 1/3 pi r squared h. But the curved surface area formula specifically requires the slant height, L. Surface area is about the outer wrapper, so you use the sloped edge. The formula is simply pi times r times L. Now, if an exam question gives you the slant height L, but then commands you to find the volume, you cannot just plug L in. You have to use Pythagoras' theorem, a squared plus b squared equals c squared, to mathematically uncover h first.
Let's look at the ultimate boss-level question for this topic. Often, an exam will show you a flat, 2D sector of a circle and tell you it's folded into a cone. It wants you to find the volume. Imagine taking a slice of pizza and rolling it so the straight edges touch. That curved crust of the flat sector just became the entire circular rim of the cone's base. To solve this, follow these exact 3 steps to bridge the gap. Step 1. Set the arc length of the flat sector equal to the circumference of your new base. Step 2. Use that circumference to calculate the new base radius. Step 3. Realize that the straight edge of your pizza slice has now become the slant height of your cone, and use Pythagoras to find the vertical height. Once you have the vertical height and the new radius, you finally have the parameters to calculate volume.
And as you are executing those multi-step calculations, remember this absolute golden rule. Keep your values as fractions or purely in terms of pi during your intermediate workings. Do not hit the decimal button on your calculator until the very end. By using exact values each time, you avoid introducing compounding rounding errors. If you round off your radius early and then use that rounded, inaccurate number in Pythagoras' theorem, your final volume is going to be completely off, and the examiner will penalize you. Leave the pi symbol alone until the final execution. Stop scrolling! Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Slicing shapes. The frustum. Now we are ready for a major structural challenge. What happens when we take a geometric blade and slice the top off our pyramid or our cone completely parallel to the base? The resulting, slightly awkward shape is called a frustum. It might look intimidating on the page, almost like a volcano with its entire peak blown off, but do not let it panic you. A frustum is fundamentally just a very basic subtraction problem in disguise.
There is no magical, ultra-complex frustum formula you need to memorize. By using the simple 3-step scaffolding, you can confidently find the volume of any frustum. Step 1. Just pretend the top is still there. Calculate the volume of the whole, massive original cone or pyramid. Step 2. Calculate the volume of the tiny ghost cone that was sliced away at the top. Step 3. Simply subtract the small volume from the large volume. Whatever mathematical value is left over is the volume of your frustum. It really is that straightforward. Find the big, find the small, and subtract.
Section 5. Tackling composite solids. Finally, let's put all our building blocks together to tackle composite solids. This is where multiple shapes are mashed together, and it's where examiners truly test if you understand the spatial relationship between geometries. When you see a complex shape, like a hemisphere attached to a cylinder or a cone hollowed out of a cuboid, run through this exact mental checklist. First, identify the core 3D shapes. What are the parameters? Second, are they joined together, meaning we add the volumes, or is one carved out, meaning we subtract? Third, and this is the vital link, find the shared dimensions. If a cone is sitting perfectly flush on top of a cylinder, they share the exact same radius. If you can find the radius of one, you instantly have the radius for the other. Calculate each separately and execute the final addition or subtraction.
Let's test this strategy. If you have an ice cream consisting of a hemisphere sitting on top of a cone, how do you calculate its total volume in exact form? Think about the parameters. The hemisphere is exactly half of a sphere, so you take your standard 4/3 pi r cubed formula and simply halve it to 2/3 pi r cubed. Next, calculate your cone's volume using the 1/3 base area times vertical height formula. Add those two chunks of volume together, and here is the link to the command word. Because they asked for exact form, do not touch your calculator's pi button. Your final written answer must physically contain the pi symbol, like 15 pi, for example.
Which leaves us with this final thought. When you sit down for your next geometry paper, will you be intimidated by these complex, composite shapes, or will you see them for what they really are? Just simple, manageable building blocks waiting to be strategically deconstructed. We've gone from the perfect curvature of a sphere down to the sliced realities of the frustum. You have the formulas, you have the strategy, and you know how to avoid the traps. Now it's just about applying them. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.